This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to go over the states of matter, heat transfer, and phase changes. The three big states of matter are solid, liquid, and gas, of course. So on our far left, we have a solid, and for chemical reactions, anytime that something is a solid, you could just see an S written in parentheses after the molecule. For liquids, you'll see an L in parentheses, and then for gases, you will see a G in parentheses. The particles in a solid are in place, but they're vibrating in place, and if energy is added, then those vibrations get stronger, and eventually the bonds that are holding the solid together will break, and then that solid turns into the liquid. So as energy is added, the solid will form a liquid. In a liquid, the molecules are still somewhat held together. They're not fixed in position. They can now move around, but there are intermolecular interactions that keep the molecules stuck to each other, which is why liquids have a definite volume. But if more energy gets added, eventually even those bonds will break, which then the liquid will become a gas because now the bonds are so weak that the particles are not stuck together and they can just move around in whatever volume they have. So gas particles are the most energetic of all the states of matter. The last thing we need to discuss is the aqueous phase. And in all aqueous phases, you will have a water solvent, and then you will have particles that are dissolved in the water. So these red dots are our molecules that are dissolved in the water. And we'll talk way more about this when we go over solutions, but whenever you see something that is aqueous, that doesn't mean that that molecule or element is a liquid. It means that it is dissolved in water. And you'll see in parentheses AQ used to represent aqueous. And for all the reactions on the MCAT, the only things that are going to be considered to be reacting are aqueous chemicals, so the ones that are dissolved in water, and any element or molecule that is in its gas phase. So later on, when we do things like equilibrium, you'll notice that solids and liquids are excluded from the equilibrium constants, and the only things that are included are the aqueous molecules and elements, and the ones that are in their gas phase. We mentioned before that as the molecules in a solid get more energy, they can become a liquid, and then a liquid can become a gas as they get more energy. And energy is gained by a substance through heat transfer. So the heat has to come from somewhere, and it is one of these three main ways. The first is simple conduction, which is when you have two objects that are at different temperatures and they are in contact, and the heat is transferred from the hotter object to the colder object. Next is radiation, which is heat transfer through photons. So you could just think of this as through light or any other electromagnetic radiation. This happens because the photons in the electromagnetic radiation have energy, and as they come into contact with molecules, that energy gets transferred to those molecules, which increases their temperature. And anytime you have an increase in temperature, what you're basically saying is that the molecules are now moving faster. The last one is convection. And convection happens whenever we have a heat transfer that's happening with a moving gas or a liquid. Here we have an object that has a liquid moving over it, and let's say that the object is hotter than the liquid. So the liquid that's in contact with the object, heat is going to transfer to that liquid, and then that liquid will heat up, but it's also flowing in this direction. So the liquid is taking that heat away from the object. Now we'll get more specific with the idea of heat transfer and the change of the phase or state of matter. So like we said before, as we go from solid to liquid to gas, the molecules are increasing in kinetic energy. So any increase in temperature means that energy has been put into the substance, and that's summarized in this equation, Q equals MC delta T, or Q equals MCAT, as most people call it. So Q here is heat, M is mass, delta T is the change in temperature, and then C is the specific heat. The specific heat is how much energy we need to increase the temperature of 1 gram of a substance by 1 degree. So if we said that C equaled 1 for some made-up substance. So if C is 1, that means we need 1 joule to make 1 gram of that substance increase by 1 degree Celsius. Because it's the energy required per gram per degree. So that's why in the equation we have the specific heat, and then all we do is multiply it by how many grams and how many degrees we've changed it, and then that's going to give you Q. And Q is the amount of heat that's been put into a system, and Q will always be in a unit of energy. So most of the time that's going to be joules or kilojoules. So heat is a measurement of energy, and specifically it's thermal energy that has been transferred between two substances or two systems. So we'll work through the first part of our problem here to illustrate and to use Q equals MCAT. So our question tells us that we are melting 100 grams of ice, but the ice is starting at a negative 100 degrees Celsius. So on the far left is where we will start at 100 degrees Celsius. To melt the ice, first we have to get it up to 0 degrees Celsius because that's the melting point. And you're given the specific heat of ice down here. And notice, and it's really important to always look at whatever units you're working with, notice how that unit is kilojoules per kilogram. So first just rewrite the equation to get yourself oriented. So we're using Q equals MCAT. We are solving for Q. We're trying to figure out how much energy was required to increase this temperature. So we do Q equals, and then for M, because this specific heat is in kilograms, I would recommend just changing it to kilograms. So 100 grams is 0.1 kilograms. For C is just straight up given to us, so 0.1 times 2.1. And next we have delta T, and delta T was 100 because we go from negative 100 to 0. To do this mentally, I think the easiest thing to do is 0.1 times 100 first. So that becomes 10 times 2.1 equals 21. And because the specific heat was kilojoules per kilogram, and we did switch our grams to kilograms, that 21 is kilojoules. So it took 21 kilojoules to get from negative 100 to 0 degrees Celsius for a 100-gram block of ice. Once we reach 0 degrees, which is the point at which the ice will begin to melt, the additional energy goes into making the phase change happen. And during the phase change, we do not have a change in temperature. So the entire time that this block of ice turns into this puddle of water, the temperature remains 0 degrees the whole time. You don't need to worry about the why, but a way you can think about it is that whenever temperature increases, the kinetic energy of the molecules is increasing. So the molecules are moving faster and faster. When a phase change is happening, all that's happening is the intermolecular forces are breaking down, but the molecules aren't vibrating any faster, so the temperature is not increasing. It's just the breaking of the intermolecular forces. So that means during the phase change, we cannot use Q equals MCAT. We need another equation, which is Q equals ML. It's a really similar idea to Q equals MCAT, but instead of specific heat, we use latent heat. And latent heat is the energy required for 1 gram of a substance to undergo the phase change. Let's pretend we have a substance where L equals 1. So this would mean you would need 1 joule to make 1 gram of that substance undergo its phase change. Notice how there's no delta T here because the temperature will never change during the phase change. So all we worry about is the mass that's undergoing the change. And L, so the latent heat, that's going to be specific not only for the substance, but also the phase change. So ice turning into liquid water, that's going to have a different L than liquid water turning into water vapor. And I didn't say this before, but C, the specific heat, that is dependent on the substance that you have. So we're working with water here, and it depends on what phase it's in. So ice has a different specific heat than liquid water. And liquid water would have a different specific heat than water vapor. But now let's calculate how much energy would be required to melt this 100-gram block of ice. And in the question, we're given a latent heat of fusion, and fusion is the term that is used to refer to the melting of solid to liquid. And the latent heat of fusion for ice to water is 334 kilojoules per kilogram. Again, we're working in kilograms, so I'm going to convert the grams into kilograms. So we have Q equals ML, Q equals 0.1 for the mass because it's 100 grams, times L, which is 334. So Q equals 33.4 kilojoules. So we answered the question and we got how much energy would be needed for each step. So now we would just add up those energies, which is 21 kilojoules plus 33.4 kilojoules, and that equals 54.4 kilojoules. Looking at what we have drawn, you can continue this process and take your liquid water and think about how much energy would be required to turn it into water vapor. So this arrow here would be Q equals MCAT because there's no phase change. We're just heating up a substance. And then when the liquid water turns into water vapor, you'd be back to using Q equals ml again to figure out how much heat that would take. Here are two phase change diagrams which could both come up on the test, and we'll talk about the one on the left first. The one on the left is just showing us the temperature of a substance as more and more energy gets added. The temperature on the left doesn't actually matter as long as you understand that we're increasing as we go up, because this could be applied to any substance. We're going to label where all of the different phases and the melting and boiling points occur on this graph. At the lowest temperature, our substance will be a solid. As energy gets added, that solid's temperature increases, and then we have this point where the slope stops and flattens out. So now temperature is not increasing, but energy is being added. The only time that's going to happen is when a phase change is occurring. So at that flat line, we have melting. At this second point, our slope increases again. And remember that our temperature cannot increase until all of the solid has become a liquid. So now at that other slope, everything is now a liquid. Once again, the slope flattens out. The only time we can add energy and not have a temperature increase would be another phase change, which means our substance is boiling, which you can also say is vaporizing. The slope flattens out for a while, and then at this point it starts to increase again, which means that all the liquid has turned into a gas, and then the gas begins to heat up. So the last positive slope, the substance is a gas at that point. So we could say the temperature at these 2 points, that is the melting or freezing point. So I'll put MP or FP, freezing or melting point. And then the temperature at these 2 points, that would be the boiling point. The graph on the right tells us what phase a substance is in as a result of a combination of its temperature and its pressure. You'll notice that at higher temperatures, things tend to be more liquids and gases, and at higher pressures, things tend to be more solids. The way one of these diagrams works is that you would find the temperature and the pressure of your substance. So if I just pick an arbitrary temperature, I go on the x-axis and say, okay, that's my temperature, and I'm going to pick an arbitrary pressure, and then this is my pressure. And then find where the x and the y would meet on the diagram. That would be at this point, so that means that if my substance has this temperature and that pressure, it's going to be a solid. And just to further illustrate the effect that pressure has, at that same temperature, so the temperature that we chose, if we lowered the pressure all the way down to this point, then that same substance at that temperature would be a gas instead. So temperature and pressure both have a really big effect on what phase a substance is in. There are 2 points you want to be aware of in these graphs. The first one is the triple point, which we have labeled with our purple arrow right there. And that is the temperature and pressure that give us pretty much all 3 phases at the same time. And that's all you really need to know about the triple point. The next one is the critical point. And the critical point is whenever your temperature and your pressure are so high that your substance is neither liquid or gas, and it has characteristics of both a liquid and a gas. So any point in that top right quadrant will result in what's called a supercritical substance. And I would not really worry about that vocab word, just know that that is the critical point. Lastly, we can use this graph to talk about the important terms that get used when talking about phase changes. Some of these will be very obvious, but we'll go over them. Solid to liquid is melting. Liquid to solid is freezing. Liquid to gas is boiling or vaporizing. Gas to liquid is condensing. Now for the less common ones, a gas turning directly into a solid is called deposition, and then a solid turning into a gas is called sublimation. The last thing we need to mention, if you think back to the latent heat that we discussed, that was how much energy per gram was required to undergo a phase change. And each substance is going to have 2 latent heats. There's the latent heat of fusion and the latent heat of vaporization. The latent heat of fusion is used for the phase change of melting or freezing. The latent heat of vaporization is used for the phase changes of boiling or condensing. So both those latent heats, if you notice, are used for either direction of the phase change that they refer to. And just make sure you're good that whenever a substance would be going to a less energetic phase, so like gas to liquid, it would be losing energy. And those latent heats would just help you calculate how much energy it would need to lose.